All right, so we were talking about uranium 235, and by the way, I said uranium 235 is rare. So you may have, when you've heard talk of nuclear stuff, you may have heard talk of enriching the uranium. And so the U-235 is rare, and so you have to extract it from the U-238, the other form of uranium, to get enough to use in a nuclear power plant. So we have this idea that obviously, if you're going to be extracting from energy from uranium, you have to have enough of it in order to produce what we call a nuclear chain reaction. So what did we say? We had said you bombard the U-235 with neutrons, and it starts splitting apart, fission, and in the process of splitting apart, it's going to release neutrons, which will, what will they do? Hit another atom of uranium 235, which will undergo fission and release neutrons. You get the idea. And it goes and goes and goes and goes. And so every time one of these atoms undergoes fission, it releases a lot of energy. So a nuclear chain reaction results in the fission of one atom, which releases neutrons. That's the one with the zero and the N, which cause another atom to undergo fission. And so it ends up, people understood that there was a huge amount of energy that could be harvested or utilized in this manner. And so it ends up 1942 in Chicago. They were able to try and control this. It's like, wow, how do you control this crazy reaction with really dangerous components, right? I mean, this radioactive uranium, you don't want to drive around with it in your car. I read, when was it? Last summer, this summer, sometime, there was somebody that was arrested in Oklahoma, and he said, oh, by the way, I've got a loaded gun over there, a rattlesnake in the back seat in a box. And then they saw there was something else in the back that he didn't identify. It was uranium. So don't do that, and don't be that guy. Don't be driving around with uranium. Anyway, so you have this a certain amount of the U-235 that you need. And what is that amount called? It's called critical mass. It's the amount of material that is required to maintain a nuclear chain reaction. And you know how much that is? About 15 kilograms. Now, 1 kilo equals 2.2 pounds. So it's about 33 pounds of this stuff right here is what is required in a nuclear reactor to have a chain reaction so that you can generate power. Okay, so this energy, as we said, it's used to boil water. The steam, it makes a huge amount of steam. Later on, I'll talk about how much steam is generated, gigantic amount in a very short time. But it makes steam, and steam expands and turns a turbine, and you can make electricity. So what you do is you need, we said, at least 33 pounds of this purified uranium, this U-235, and you put it in what they call fuel rods. So that you put this stuff in rods that are down there in the reactor, and then you have to have a source of neutrons to start it. Once you get it going, it's going to be self-sustaining, but you have to have a source of neutrons. And so we have some other really fun elements. Plutonium, it's a very dangerous element, but it emits neutrons. And it, or beryllium, another radioactive substance, these are what are used to start the reaction, to start the chain reaction. So you have fuel rods that contain this uranium oxide. And then you have something else. We said you have to have a controlled reaction. In order to control it, you need something that will absorb the neutrons and keep them from bombarding the uranium if you want to stop it. So you have to control it. And these are what we call control rods. And these are made of graphite. So you can put the control rods down in between the fuel rods and stop the neutrons from flying around and causing nuclear fission. Okay, so whenever you want to turn the reactor on, you pull the control rods out and you let the reaction begin that way. Okay, so you may have seen pictures of nuclear reactors. It's not like this is out in the air, right? They have a swimming pool. It's in a swimming pool, but you wouldn't want to swim in it because it's not just regular water. It's a boric acid solution. So all of this reaction is happening in an acid water type solution. And it's under pressure. It's a pressurized chamber where this is happening. It's pressurized at 150 psi, which is a lot. 150 atmospheres. And so then the heat that is generated by the steam is transferred through a heat exchanger, and this is how, so the really hot boric acid is passed through some pipes in water, and it boils water and creates steam. There is a reactor in Seabrook, New Hampshire, and I think that's where they're talking about. Yeah, Seabrook Nuclear Power Plant. Every minute, when that reactor is running, every minute it generates 30,000 gallons of steam. As I've said, a huge amount of steam. And this steam is used to generate electricity. And it uses 400,000 gallons to cool the steam. So after you've passed the steam through the pipes and it turns the wheel that makes the electricity, you have to then cool it again. And they use the 30,000 gallons of steam is cooled with 400,000 gallons of seawater. Seabrook is right on the coast of the Atlantic Ocean. Okay.